our high school Slimsat Space Initiative 26 meeting. My name is Garth Likens, Program Manager for CAPE. We have our CAPE-Twiggs CubeSat, some of our CAPE-Twiggs CubeSat project team here. Dr. Paul Darby, Miss Melissa Poore, and everybody else here who is participating. So today we have an exciting topic. We have a guest speaker, Dr. Paul Darby. Dr. Darby is the PI. He is the PI of the CAPE-Twiggs CubeSat project. That's principal investigator. He wrote the proposal that NASA said yes to, along with a little help from other people. Dr. Paul Darby holds a bachelor's degree in electrical engineering, a master's in telecommunications engineering, and he's got his PhD from the in computer engineering from the Center for Advanced Computer Studies over here at the University of Louisiana at Lafayette. Dr. Darby's research interests include mobile decentralized computing, mobile cloud computing, mobile grid computing, swarm robotics, and satellite experimental smartphone grid technologies and engineering, thereof which he holds 5 patents. Some highlights from his career include he worked as a math teacher, teaching high school algebra and trig at a Catholic high school in Louisiana. He worked in the oil and gas industry in the Gulf of Mexico and in Hong Kong. He's got 10 years in aerospace on the Space Shuttle program as a systems engineer in failure modes effects analysis and human factors. He received the Silver Snoopy Award, the highest award given by NASA to a civilian, in 1985, presented to him by astronaut Marcia Ivins. In computer networking, Dr. Darby was one of 8 engineers to put Louisiana on the internet in the late 1980s and the early 1990s at the State Computer Network, LA-NET. Dr. Darby ran his own company for a while after selling stock in a previous company, Icon. His company title was PGG, Pretty Good Guy. He joined the University of Louisiana at Lafayette in 2002 as an instructor to become assistant professor in 2013. He got involved in the CAPE CubeSat program in 2004 and has participated continuously since then. He's a registered professional engineer in the state of Louisiana. Him and his wife, Regina, live in Lafayette, Louisiana. She's a nurse. They've got 2 daughters. Janique Darby, if I'm saying that right, Dr. Darby, please correct me, is an associate professor of linguistics in Volda, Norway, having received her doctorate from the University of Oxford in the UK. And Victoria is a medical assistant at Our Lady of Lourdes Medical Center here in Lafayette, Louisiana. So thank you very much, Dr. Darby, for volunteering to, give us your wisdom today and your experiences. I understand you're going to be speaking about the engineering design process and other things. So without further ado, Dr. Darby, I will let you have the floor.
Okay, good afternoon, everyone. Can everyone hear me? Okay, great. So let me start off, preface my presentation by saying, first of all, I'm human and I make mistakes. Okay, and so that'll kind of lead into some of the things that I want to talk about. So we're all human, right? And because we know we make mistakes, we can take measures to mitigate the effects of those mistakes, and we can take measures to help prevent ourselves from making mistakes. And maybe we can check on our teammates too to help them reduce the amount of mistakes they make, right? If NASA knows anything, it knows that people make mistakes, and they put processes in place to help root those out. Okay, so I want to start off by thanking my mentors that I started out with as an engineer in my younger days. One of my favorite people in the entire world was Mr. John Christopher, who was a human factors expert that I met in New Orleans at NASA Michaud. So at NASA Michaud, I don't know if you're aware, but in New Orleans, NASA Michaud has had a role in every space program, manned space program that NASA has done, from building the first moon rocket boosters to now working on and building the Mars rockets that will take us to Mars. And John Christopher was integral in a lot of that. He was a human factors expert. He had degrees in psychology as well as engineering, and he was involved in the space shuttle project and many other projects you might be familiar with from our arsenal, our weapons arsenal, in the energy field. He even had a role in helping to shape the movies, right, and television series in the early 1950s. The ray gun used by actor Cliff Robinson in the CBS fiction scene, right? Red Brown of the Rocket Rangers, right? So he's had a big role in things. Now, one of the things that made John so passionate about human factors was that in his younger days, he actually was exposed to high intensity X-rays because of a human error, and it caused cancer. And for years, John lived with and fought cancer for many years until it finally got it, right? So it finally got him, and but he and I had a good opportunity to build a friendship and a mentorship. He was one of my mentors. Next one was a guy named Ukrainian-born, Ukrainian American engineer named Bo Beamick. Bo he personified the word systems engineer, which is the aerospace term that's used. He and I met in Los Angeles, California, when I and he both worked for Rockwell Space Systems Division there in Downey, which is a suburb of Los Angeles. But he taught me uh, everything about systems engineering. He was also later involved in a project called Sea Launch, where an offshore oil platform, a floating platform, was brought out to the southern Pacific, a place near the equator, to launch rockets, putting satellites into geosynchronous orbit more efficiently and more cost effectively. So that's Bo Beamick, right? So he was one of the principals involved in Sea Launch. Next slide I wanted to show you is one where things didn't quite work out well for me here in this slide, but it was one for Wile E. Coyote, right? If you've ever seen the Roadrunner cartoons, he's always coming up with these contraptions and buying his parts from Acme Manufacturing to create these contraptions to get the Roadrunner. And of course, he's a genius, so every contraption he builds, it's going to work out perfectly, right? Of course, it never does for the coyote in the end. Uh, but but he's Mr. Know-it-all. He knows it all, and so he can't really learn and correct his mistakes going forward. He already knows everything. He's the genius. Um, and I want to say, I've every project team I've been on, there's been some person who or persons who have a little bit of Wile E. Coyote in them, and so we have to be mindful of who those people are on our team. The person that I guess that feels they can't make a mistake is one that is going to make one, and they're going to make a disastrous one. So we need to be mindful of that. Uh, Now, no design is perfect. We can work on designs and progress towards perfection by continuous improvement. Um, I'm not too impressed strictly by cool technology unless it works consistently. Consistently. My saying here, technology is great when it works. It's also great when folks can use it. So if you look over left, this is a perfectly designed door, right? Yet the guy can't reach it. Or maybe if he tries to reach it, he'll make a mistake, right? Um, we have to consider who's going to be using our designs, and how many areas can our someone on our team make a mistake from the design, the calculations, the coding, the assembly, the testing. At every one of those levels, people can make mistakes. But we can do designs and have put processes in place to reduce the probability of those mistakes happening. Okay, so it's about the process. In designing a system, we need to build in many factors in the process, even human factors. But the process normally starts with the client requirements, or maybe some science drivers, or technology, demonstration drivers, or economic drivers, or even economic constraints, or a problem that needs to be solved. So that's where we start. So that's our step one, but it's a process. And I think the process is even more important than the product. Anybody can have beginner's luck and create a working product the first time. But to consistently achieve working products and resilient products and robust products, we need a process in place. Let's see, I think we have a little bit of a delay. Okay, let's see. No, okay. All right. Go back here. All right. All right. So the next step, though, after you get your client specifications or your client requirements for the project, is because you don't know everything, you've got to do some research. So where do we start with our research? Well, fortunately, these days there's plenty of sources for information, and we need to make available those things. Well, somebody might say, "Well, I already know how to build this. I don't need to go to the library. I don't need to look at papers on Google Scholar. I don't need to talk to mentors or experts or peers. I don't need to look at data sheets. I don't need to look at component data sheets and characterize those components before I use them. I already know all of this stuff." Okay, we have to avoid that temptation. We've got to, spend some time in the library, spend some time looking at papers that discuss our subject. It's a big planet. Lots of people are working on lots of things. Don't reinvent the wheel. Uh, and also you want to talk to those experts and peers and find out what you don't know. All right. What we don't know but think we know is probably the worst part. So next step, we need to establish a project philosophy. Yes, I said philosophy and ground rules. Not all projects are created equal. We need a philosophy as to how we're going to conduct the project. Is our project have a short time fuse? Is it economically constrained? Um, is it critical? Is it a critical project, or is it just something that some gadget we want to show? Um, but we need to establish those philosophies and ground rules. One important one that we've had to establish on CubeSats is we only want to take team decisions as approved, not individual ones. We don't want individual people going off and actually making decisions about the architecture or the design without the team being involved. There needs to be debate on this. There needs to be peer review on this. We need to define the roles of people on the team. We need to have project procedures, how to conduct the project, and we need to have approvals for every major decision that's taken, every major action or path that we take. And we need to have some quality standards and procedures about quality. Let's see here. Oh, okay. The next thing, let's see here. Okay. All right. Trying to get one ahead of myself here. Okay. Um, okay. So next step is we need to do step 4, we need to do some synthesis, some brainstorming. Synthesis is imagining what kind of system, and what we're designing is a system, what kind of system will solve the problem? Um, and we need to make some drawings of that system. We need to describe how it's going to work. Just as if you would on your kitchen table, for example. Don't worry if it's not perfect, it never will be. So, welcome to design. You've just created your initial design concept, drawing, and system description. In your system description, you should describe how your system will function and to what performance levels or requirements. Then, similarly, describe the subfunctions. Uh, Use concept drawings to create what we call a level 0 functional block diagram. This is a single block allowing you to know what the boundaries of your system are and what their interfaces with the outside world will be. Speaking of interfaces, the next step is to do system decomposition, which means divide and conquer. You want to divide your system into smaller logical subsections or subfunctions. For example, power, computing, communications, mechanical. This was referred to as functional decomposition. And that's very important because you might have different teams with different expertise working in different areas. Computing people working on computing, power people working on power, and they're getting work done in parallel. They're getting work done simultaneously. Then step 6, very important that this comes early. Define all of the interfaces between the outside of the system and between any subfunction and interface interconnections between subfunctions. That way, while the work is proceeding in parallel, the teams and the separate teams can be something happened. Okay, let's see here.
Stephanie,
Did anything?
you're sharing.
Okay, so I guess let's see if I can share it again. Okay,
There
let's
we go.
go.
Looks like it popped back up.
Okay, can everybody see my slide on the interfaces and functional and system decomposition?
Yes, I think we
Okay.
can. Yep.
Okay, so step 6, we want to define all of our interfaces. What do I mean by interfaces? Any access point or any function that accesses our system from the outside, or interactions that are going between subsystems or subfunctions. For example, we have solar interfaces on the satellite. All right, sunlight is going to be impinging upon our satellite. That's an interface. Signal interfaces are radio interfaces, radiation interfaces. Between all of the different subfunctions, mechanical, electrical, data, pressure, fluid, thermal interfaces, all of these are interfaces between subfunctions within, say, a CubeSat. And yes, human interfaces. So why do we want to define the interfaces firstly? So that each of our subfunction teams can be building to those interfaces so that when they're complete, they can seamlessly integrate together. And if I don't specify that ahead of time, we're going to have problems when we try to integrate all of those subfunctions together and get them to work together. They'll be designed to different interface standards. We need to have them all speaking the same language between, or following the same standard between subsystems and between the system and the outside world. The next thing we should do is consider alternatives and trade-offs to meeting the subfunctions of our design. So this is where we have characterized components whose behavior we may have characterized in some way, either through looking at the data sheet or running some tests on these components. And we want to select the best components to do the job of the subfunction. Sometimes cost might be a factor. Sometimes experience with those components might be a factor. Sometimes the reliability or the the adaptability of those components might be a factor. Once you have these selected, this is an alternatives and trade-offs. You have to list the pros and cons of these components that you're using to comprise the subfunctions. Once we have that done, we probably want to look at more detailed drawings showing each subfunction and how they interface to the outside world and to each other. And then we prepare something called a level 1 functional block diagram, which shows all the interconnections and what those interconnections are carrying. Is it data, power, what voltages, what pressures, what mechanical interface, and so on. We've got to show that too. And then here's where the real design step comes. Up to now, we've done synthesis. Now we're going to take our synthesis hat off and put our analysis hat on and start looking at the design concept we've come up with and its details to validate that design concept and to verify its function too. So what are some tools we can use for validation? Well, we can, and first of all, by the way, all of these apply to doing peer reviews as well. So you should actually, the same person who designs the system should not be the person who reviewed it. Nobody likes to call their baby ugly. Somebody else might call it ugly, but you won't, right? You're always proud of your design and you can't see its flaws or mistakes. Somebody else can do it, right? You want to have somebody review your drawings for accuracy and appropriateness, right? Calculations. Maybe there's some calculations that need to be done, or maybe you've done some calculations. They need to be reviewed. You might have done some simulations, or you might need to do some simulations to validate your design. Will this work in a simulator? Simulations are a lot cheaper than actually prototyping. If you can do a simulation that's realistic, it's cheaper and faster, and you can make changes and you can try a lot more options. Then for coding, and I see this done all the time, I see people start coding without any flowcharts defined or without any state machine diagrams defined. That should never happen. You should do some flow charting to validate your software approach before you write the first line of code. You should do some state machine diagrams to do the same thing. Before you use any parts in your system or select any parts, you should do some characteristic testing. If you don't understand how a part behaves, you shouldn't make it part of your system because your system will be unpredictable then. You've got to understand down to significant detail how your part will behave as part of your system. Some other techniques are specialized techniques applied to design by systems engineering. They include hazards analysis, failure modes effects analysis, complexity analysis, and complexity reduction analysis. How many people here know what NP complete is when we're talking about computational complexity? So I'll give you an example. We've had a situation at NASA where we had a chip with 100 input pins and 100 output pins. Somewhere in that chip's logic was a problem. It's a new chip. We want to test it. We want to see if there's a disastrous output given some particular combination of inputs. So one way to try and determine that would be to do some brute force testing. I'm going to test digital combinations across all 100 input pins, right? Actually, if you did that, even if you could do 1 billion trials per second, 1 billion trials of different inputs per second, To complete the test would take you 40 trillion years, because you're talking about 2 to the 100 power combinations. So by brute force method, you could never really, and because of the computational complexity here, you never really could exhaust all the combinations. You really might never find the bad apple in all of those combinations. So what are you supposed to do? Well, a solution to that is to only use the combinations that you've tested and to null out all the other combinations. That way you know what you've tested is tried and true, and you can use that, right? We need to consider the human factors as well. But by the way, every piece of software of any significant size is NP complete in its complexity. And you never really can find all of the bugs in a piece of software. Mathematically, it is impossible because of this. So what you have to do is limit the inputs to your software and limit its outputs in order to make that software hardened. Okay, and again, all of this should undergo peer review. Let's look at an example of hazards analysis. So here's one where the mission is to transport the crew to the ISS. We want to launch the crew to the International Space Station. We want to stay docked to the space station for 6 months, and we want to return the crew to Earth and land in the water. What are some hazards associated with this? This is where the brainstorming comes in. Okay, look at this. This is the short list, really. Collision or impacts. Well, I guess both with the space station and with the crew. Loss of control, contamination, corrosion, electric discharge or shock, environmental weather, temperature extremes, gravitational forces, electromagnetic interference, radiation, that's a big one, explosion, fire or overheating, flight termination systems, and others that would go, loss of habitable environment, psychological, pathological, psychological, or physiological problems, right? Lasers, utility outages, loss of structural integrity, loss of critical function, loss of safe return capability. And there are many more that you could probably think about here in your hazards analysis. What's the purpose of the hazards analysis? It's to identify the risks and put us on the path to developing means of control or eliminating the hazards where we can. We might not be able to eliminate all of them. We might not be able to reduce all of them. But unless we know what hazards are out there, we can't begin. Let's look at human factors. Human factors involves lots of subfields. For example, we might have computer science, cognitive science, clinical psychology, experimental psychology, anthropologic science, where the function of the human body, safety engineering, organizational psychology, and so forth, industrial technology, medical science. All of these are involved in human factors. Think about people that are working on the design of your project or assembling that project. What's their physical state? What's the environmental conditions? I know myself, I can't, when I'm doing fine detail work, I need a well-lit area. I can't just do this in a dark room, right? Those environmental conditions of how we do our design are very important. What's my mental state? Am I tired? Do I have any human limitations? Is my vision blurry? What's going on? These are all factors in the design process, the coding process, the operational process. These are things that can lead to mistakes if they're not carefully controlled. Next is the failure modes effects analysis. So I captured this from Goddard Space Flight Center. I did a lot of this kind of stuff when I was with the space shuttle program. A failure modes effects analysis is not, in a failure modes effects analysis, we don't go and actually fail components and see what happens. We go and hypothetically fail each component. And then we look at the failure mode of that component. For example, how does a processor fail? I thought about this a lot. One of the easiest and nicest failure modes might be the processor just dies. It just stops working. Oh, I would love that kind of failure mode because I could just switch in a new processor automatically and keep on going. But a lot of times, processors fail in a very nasty way. They have subtle failures, might be induced by radiation of logic or corruption, and they might make changes to our software output that we might not even detect. The first thing is we'll have to be able to have a way of detecting that processor failure and then seeing if we can take mitigating action. You may or may not be aware, but the space shuttle itself, or in its guiding computers, had five computers, five identical computers operating in a voting logic. Um, and the results were compared computer to computer, and best 3 out of 5 wins in making the decision. Years ago, there was actually IBM underwent a study to run long-term computing programs, and one of the programs was calculating, for example, the number pi to trillions of places. And over a year time frame, what they found was that if they run several computers, they would get different results at different iterations. What was causing that? Well, actually, they theorized that it was radiation coming in through the Earth's atmosphere that actually was flipping bits somewhere in the computer memory. So computers are not necessarily guaranteed to produce the same results every time. The same thing has happened on aircraft on occasion. Um, the computers producing different results, and the results, the effect might be unknown origin. Okay, so to continue our analysis, we use these analytical results that we've gotten from human factors, from hazards analysis, from failure modes effects analysis, from our peer review, from our software validation and verification to improve our design. Our goal is zero identified defects. Uh, at this time, it's also vitally important to control and limit the changes and enlargement of our scope. Sometimes folks will try to bring in new technology that they are enamored with to change the project. Right? Well, you've already done a lot of analysis. The later you go in your project and then you make a change, the worse it is. And you've got to go back and do this analysis over, right? You want to resist that. You want to resist scope creep. You want to resist it adding to the complexity of the system. Okay. So now it's time to start building your system. Integration. We want to start integrating the system from the component level to the subsystem level, to the subassembly level, and finally the system level. And at each step, we want to test. We want to test our components to make sure the components comprising a subsystem are good and validated. The subsystems comprising a subassembly have been tested and validated. And then the system itself is tested and validated. At each step, you might uncover new problems, at which point you've got to resolve those problems before you go on and continue to comprise and integrate the system. We call this, finding these problems the root cause. We're looking for the root cause of the problem at each step when a problem comes up. Now we want to go into once we've done this, we rinse and repeat and keep doing this until we actually have zero identified problems. We come to the acceptance part of the process where we review this with our client, or we might have had that client review as a reviewer along the way. And the final step in the process is you need to document everything, the drawings, the specifications, the code, the testing, right? Uh, so that others can build on that knowledge. This is called an as-built. Um, so we've got to go through the software the same way, just as we did all of the hardware. The software is not immune to this. In fact, much of the design is written in software, and that's just as important, or even more important, than all of the hardware that we're dealing with. And all of this, the code, the hardware, has to be accepted, and all of the bugs and that we can determine, all of the problems that we've determined at every level, from integrating code modules together to whole blocks of code, um, need to have been complete, and the problems identified and eliminated where we've discovered them before we accept the system. Don't accept the system too early. All right, so finally I have a few some food for thought sayings here. Um, if humans were all knowing and never made mistakes, there would be no need for a design process or procedure. We just put a system together and it would work magically and consistently, uh, without any other thought to it. But we do. Humans do make mistakes. Another one here. Complexity is the enemy of reliability. This is my quote. Uh, Technology is great when it works. Everybody makes mistakes, but to make disastrous, far-reaching mistakes requires a computer. The definition of genius is taking the complex and making it simple. Albert Einstein. The definition of insanity is doing the same thing over and over again, but expecting different results. Also Albert Einstein. And my comment on that is, Einstein obviously never used a computer, because we've done the same thing on computers at times and gotten completely different results, right? There are different results each time, and all of that happens to be because of unknown variables, latent defects, latent changes in the code that we weren't aware of. Okay, and to conclude, I've added some links here for things that you might want to be able to look at. I put in here a link to NASA Handbook of Systems Engineering. I have a talk here by my former mentor, Bo Beamick, about his systems engineering solutions to some problems in the early days of the space shuttle program. And finally, I have a space shuttle launch video from the view inside the orbiter. Okay, that's it. I'll take or entertain any questions. Of course, I'll share the slide presentation with you if you want more details or you have more detailed questions. I'm happy to help or happy to provide information. The end.
I do want to say thank you for this high level version of the engineering design process. We do teach that in high school very rigidly, but at a different level. So it is really valuable to get this perspective as we launch our own mission. So, yeah, I look forward to using these slides with my group.
Okay.
Thank you.
So I tried to keep it as simple as I could for now, and make it palatable, um, for student consideration. And I don't want their eyes to glaze over. I want them to see that, because most of them are very enthralled with the coolness of technology. But you'll never realize that coolness of the technology unless it works. And we've got to make sure it works because um, in orbit, we can't send the Maytag repairman there to fix it. It's got to work automatically. It's got to be to some extent self-healing, uh, and resilient to failure, right? Otherwise, you have a brick instead of technology, and a brick is not very exciting.
Mhm.
So,
Well, as I do want to say to the participants, as we, prepare to engage with the hardware and do quality assurance testing and start to, anticipate this human factor. I mean, this is a real thing that as a teacher, we can't really always build into an engineering design challenge, but we must certainly for this, for a space mission. And what you said about the prototyping simulations being so much cheaper, faster, and that value purpose for that step in the mission, that was very relatable. Uh, Thank you so much.
sure.
Yeah, does
So,
anybody else have any questions or comments or
and
thoughts?
don't be afraid to ask, because again, I make mistakes. I'll try to give you the best information from my knowledge, but I do make mistakes, and I wasn't always all knowledgeable, uh, of this stuff. I know what I needed to function as a NASA systems engineer. But again, even NASA systems engineers have lots to learn.
um, my students were really focused on the Starliner um, ordeal and the political talk about how to bring them home and all of that. And then most certainly the Blue Origin all female launch Monday.
Right,
So talking about the human factor and how can systems help compensate, because we need humans. We need their brain for, that high level processing during making that human choice. But it's really interesting to think about how robots, AI can help compensate for that natural error, right?
right,
And
right,
you were talking about the planes, right?
right,
And those systems um, really advancing us being able to take flight and
right,
by large quantity of people,
right,
because human error, an automobile on the ground is less forgiving. I mean, it's more forgiving
right,
than human
right,
error up there. So
right.
big changes in cockpit design, and you were
Hmm.
talking about the interface,
Right,
um, ergonomic planning for what's
right,
easiest to see.
right.
Um,
So
yeah,
example,
it's really interesting to. Mhm.
would be, on a jet airliner, for example, the buttons to turn off engines are recessed into the above head panel. And so in other words, if a pilot's taking off his jacket or moving his fingers around, he can't accidentally turn off an engine. He has to stick his fingers into the holes and actually be intentionally turning off those engines. So the design is done in a way to prohibit accidental, uh, killing of an engine. In the space shuttle orbiter, the hatch, if the hatch is blown while the astronauts are in orbit, it's instant death. You've lost your atmosphere in the space shuttle. There's a button on the hatch that you can press to blow the hatch. And however, that button is not armed unless you pull the mechanical handle out, turn it around 2.5 times, and latch it back in. You can't blow the hatch by accident. It has to be intentionally done. So we don't even have to go as far as AI to try to mitigate or prevent human mistakes. We can actually do that in some very, very simple ways. Uh, in addition to training, but there's ways you can design a system such that you cannot connect it the wrong way. So a simple one we have on our batteries, for example, all our batteries have keyed connectors so that when I plug in a battery, I can't reverse the polarity to, say, my computer or whatever. It can only be plugged in one way, and I can't reverse the polarity. You know, if you reverse the polarity to your computer from the battery, you've burned the computer. But the keyed connectors prevent that from happening. That's considering human factors. We can't plug it in backwards, right? We can't use it in the wrong way. A lot of that is built in, right? Sometimes we build in such that human factors such that it requires teamwork. So to get access to one panel, you have to get a team member to agree that what you're trying to do is appropriate. These are things that can be done, many things that can be done even without AI. AI will be a help, uh, but AI also comes with some baggage, and we have to be careful that when we're employing AI, that is fully vetted, that we're vetting that, right? Remember, AI is very complex, so the complexity alone makes it something that we have to be a little bit wary about. Yeah. So yeah, Einstein obviously never used the computer, so he's, you know, he'll think that, you know, if you do the same thing, we should get the same result each time.
Yeah, some of the students came into the lab this morning, and the thing that was working yesterday, which was a computer, hadn't done anything to it, is working totally different this morning. Didn't
Yeah.
do anything different.
Well, sometimes say third time's the charm. Reboot it 3 times and it'll start working again.
All right. Going once, going twice. Thank you so much, Dr. Darby. We
Sure.
appreciate your presentation.
Anytime.
Um, and we look forward to more interactions like this. Uh, we will have another meeting next month. Dr. Kevin Crosby will be our guest speaker. Uh, in other news, we have an alpha version of our Slimsat that's being engineered and tested by certain peoples in our group to hopefully make one for actual distribution that will be easy for everybody to use and play with and engineer. So we thank you all for being a part of this meeting. The recording will be posted on YouTube, and I'll send out a follow-up email, hopefully sooner this time than it has been the last few times, with a link to that and information for our next meeting. And so, everybody, thank you for being here and have a wonderful night.
Thank you, Dr. Darby. Thank you, Garth.
Absolutely.
You're welcome.
Thank you.
Good night, everyone. Yes, good to see everyone. Thank you for joining.
Thank you.
Good night.